So do you see the screen?
Yes, Victor.
Well, so let us continue discussing the economic dispatch problem. The economic dispatch problem, simply the objective is to dispatch the load among the committed generators. So we have discussed some cost curves of the generator of the generations, like incremental cost curve and cost in dollar versus megawatt hour. Also heat rate curve and other, as we discussed last class. So we have the problem economic dispatch is an optimization problem where you want to find the power output of each generator in order to minimize the overall cost or the fuel cost. So this will give you, of course, the most profit operation scheme. So it is an optimization problem, and we will, in this class, we will give you some brief introduction, which you already covered in calculus, how to find the minimum value, how to find the solution that gives you minimum cost function or objective function. And we will see how to formulate the problem of economic dispatch as an optimization problem. And then we will see how to solve this problem to find the optimal scheduling or optimal dispatch among the generators available. So mathematical formulation of the costs, as we mentioned, cost could be a linear function in the power, could be quadratic function, could be cubic function, could be, as I mentioned here, probably in this figure, you see this figure, right? Where you have here some nonlinearity due to valve opening, and probably in the previous slide we talk about if you have fuel switching, if you switch between certain fuel to another fuel, from crude oil to whatever oil to gas to this, so you have different cost functions as such defined on a certain period here of output power. So you have some kind of non-smooth or discontinuous cost function. طبعا this will complicate the problem solution, but in our course we will use only the quadratic function as such, without any nonlinearity, without any non-smooth effect of valve opening. So we have here cost is function of B, a quadratic function of B, alpha constant beta PG plus gamma BG square. And the incremental cost, IC as we defined earlier, incremental cost, you take the derivative of this B, of this cost over B. So you have here, this will go and this will be equal to beta only plus 2 gamma BGI. So this incremental cost play a great role in optimization, as we will see later. And the physical meaning of the incremental cost is, as you can see here, dollar per megawatt hour. So this value, if BG equal to, for example, 2 mega or 6 mega, and 6 mega, 6 multiplied by 0.2, so this will be 1.1 times 2, so will be 2.4 plus 5 يبقى 7.4. So 7.4, or here we have give an example if BG equal to 10, so the incremental cost is 9. So that means you will pay $9 in order to increase the output of the generator by 1 megawatt hour. And 1 megawatt hour will cost you $9 increase. This is the physical meaning of the incremental cost. How much you will pay for 1 megawatt hour generation. Okay. This is just a very simple example. Probably we covered it last class. For a 2-generator system, assume that the cost of the first generator, BG1, function of BG1 equal to this, and the cost of the second generator is equal to this function. So if you have BG1, or if you want to get the incremental cost of the first generator, second generator, you just get the derivative of this with respect to BG1. So it becomes 20 plus 2 times 0.1 BG1. Or second one also derivative, this will go. So it becomes 15 plus 2 times 0.03 and 0.06 BG2. So this is the incremental cost of this generator. If you have a specific value of BG1 and BG2, you can calculate how much cost and how much incremental cost at this loading level. So if BG1 equal to 250, you will supply here by 250. So you get the cost of the generation is $6,625 per hour. So this is the cost, dollar per hour. And the incremental cost in this case is 250. So you substitute here, you will get $25 per megawatt hour. So if you want to increase, for example, from 250 to 251, and you increase the output power to 1 megawatt hour, it cost you $25 more. So this is the physical meaning of the incremental cost. So for the second generator, if you have BG equal to 150, and you have here 150, you substitute, you get the cost equal to this. For the incremental cost, you substitute also 150, so you will get 24 megawatt hour. So let me ask you, at this point, this is the incremental cost for BG1, and this is the incremental cost for BG2, for generator 2. Now, if your load here, assume that these two generators are running in parallel in power system, and this one produce 250 and this one produce 150. So total load that you have is 400 megawatt here. If the load increases to 401 megawatt, assume that load increases by 1 megawatt. So this 1 megawatt, you will generate it from where? Generator 1 or generator 2?
Generator 2.
Generator 2. Why?
Because
cheaper at this level of, خلي بالك, at this level of generation. At this level of generation. Maybe if we have different pattern of generation, like this is 250 and this is 200, maybe the lambda in this case will be higher than generator 1. Okay?
So we should check the incremental cost.
Exactly. For example, if this is at this level of generation, these are the incremental costs. So if we need to increase the power by 1 megawatt, definitely we'll go to the generator 2, which is cheaper in this case. But assume that different pattern of loading. And you can here say if BG1 equal to let us say 300, and the BG2 let us say 200. Hopefully this will validate the point I want to emphasize. So at this level of loading, how much IC1? This will be 300. 300 multiplied by 0.02, it becomes a 6, plus 20, it becomes a 26. IC2 for this level of 200 multiplied by 0.06, it becomes a 12, plus 15, it becomes a 27. Oh, in this case, you can see here, generator 1 at this loading level becomes cheaper than generator 2 if you want to generate 1 megawatt additional, right? Is it clear?
Yes, yes, it's clear.
Here the clear is you can see here the importance of having this incremental cost calculated at the dispatch or the scheduling of the output power of generation. So in this case, for this pattern of loading, the generator 1 becomes cheaper, and if we need to load here is 500 total. If the load increases by 1 megawatt, definitely will go to the generator 1 to produce. Then this will be cheaper than. Okay. So let us formulate the economic dispatch problem as an optimization problem. The optimization problems is very simple, and typical formulation is you have a cost function, you need to minimize or maximize. Definitely you can have also some cost function to you need to maximize. Okay, maximize or minimize. Cost function, objective function, function of some of the variables. What we have here in economic dispatch, these variables are BG. Our BGs, and we have one generator, second, 2, 3, 4, 10 generators, so we need to optimize this output of the all generators. So we need to minimize, or if we say cost, we need to minimize definitely. But some of the objective function you need to maximize. For example, if you need مثلا to check the reliability of the generator of the power system, in this case you need to maximize the reliability. Okay. Other objectives also can be defined that needs to be maximized. And typically we have minimize cost, subject to means then we have some constraints. We have some constraints here. And these constraints are function also of X. For example, in our problem, we can say in the BG1, B generator 1, should be within certain bounds. This is a constraint. Okay, BG1 minimum, and we have here BG1 maximum. So each generator has limits from 20 megawatt to 100 megawatt. Above that, you cannot get. Below this, it's better to switch off the generator. So you have a limit of BG of each generator. So this is some kind of constraints. So the constraints also function of X. Solution of this is how to find X. This is the solution. How to find the power output of each generator. This is the solution in order to get minimum value of C, and at the same time you satisfy all the constraints. Okay, so this is simply the solution. The solution is find X that gives you the minimum value of the cost, and at the same time it satisfies the constraint, should satisfy the constraints that you set here. This is simply the optimization problem, an objective function and sum of constraints. Okay, if you have any question, please ask. So here, probably we'll cover this point here. Okay, the goal of the economic dispatch is to determine the generation dispatch that minimizes the operating cost, subject to constraints that total generation. This is one of the constraints. This equality constraints must be satisfied. And the total generation summation of all BGs equal to load plus losses. The total load plus losses. This is must be satisfied, and also you can have other constraints related to the limits of the power output of each generator. So simply the economic dispatch problem is as such. You minimize the cost, and this cost is a function of BG, like a quadratic function that we discussed in the previous slide. So this is the cost as a function of B, and this is the constraints. We have here equality constraint. This is equality constraint, and this is inequality constraints. So we have to satisfy the equality and inequality constraints here. Summation of BG, M is the number of generation, or number of generators. So summation of total output power from the generator is equal to the demand plus losses. And also each generator must satisfy the bounds here. So this is typically of course the problem can be simplified and can be complicated as well. And you can add some constraints here to complicate the problem. You can add, for example, line flows. S line must be less than or equal the line maximum flow. If you have a transmission line, so you cannot, for example, if you have a generator here and you know the limit of this transmission line is 100 megawatt. So in this case, even if this generator can generate up to 150, but in this case 150 megawatt, in this case you cannot operate the generator here for more than 150 megawatt, and this line will not be safe if you increase power over the 100 megawatt capacity of the line. So you can also complicate the problem by adding some other constraints. You can say, for example, voltage at all buses must be within the bounds 0.95 to 1.05. So in this case, this is other constraints, and if you increase the number of constraints, you are complicating the problem. You are minimize the search space of the optimal solution. Okay, and you complicate the problem. Of course, we need to start with the very simple formulation, and then we can start incorporating the constraints one by one. The first simple, or the most simple formulation is to neglect the losses. Assume that a new system is lossless. This is impractical, but this is for mathematical necessity, in order to simplify the problem. And in real life, losses is there. We cannot, of course, neglect it. And also we can neglect this constraints at the time being. And we have the objective function. We need to minimize the cost, assuming that the number of our total generation equal to the total demand. This is the most or the simplest formulation of the economic dispatch problem. And you have a cost function and you have very simple equality constraints without any incorporating any network or generator limits. Okay. So we can spell it out here. The objective function equal to the cost, total cost, which is the cost of generator A, cost of generator B, cost of generator C, and each cost is a function of the power output. Could be quadratic function, could be cubic function, as we mentioned earlier. But I know we will stick with the quadratic function, which is more or less simple one. The constraints, the total load plus losses equal to the summation of generations, and unit constraints BA, BB, BC should satisfy the bounds here. So definitely, as I mentioned, we will start with the simplest formulation. We will initially ignore the generator limits and the losses. We will take this out and also this out. So we have very simple optimization problem, and then we can see how to solve it. Later, we will introduce these, constraints one by one. So the simplest formulation of the economic dispatch is as such: minimize the cost, summation of number of generators, and each cost is a function of this power output, subject to summation of generation equal to the demand. Okay. طيب, in order to solve this problem, we need to give you a brief introduction about the optimization. We have two types of optimization: unconstrained, you have only the objective function, there is no constraints here, and constrained. If you have constraint, how to handle these constraints? If you have equality constraints, how to handle this? If you have inequality constraints, how to handle such constraints? So we will give you a very simple, very brief introduction to optimization, and actually you covered it in calculus. Very simple. If you have مثلا cost function and we define a cost function as x squared, can you minimize this function? Can you minimize this function? Can you minimize x squared? Yeah, definitely you can say no. X squared is a minimum if x equal to 0. So this is a solution which gives the minimum cost. Okay. So if x equal to 0, then cost function will be 0. Otherwise, x if x takes any other value, then cost will be higher than 0. So this is simply the solution. Of course, this solution in calculus, you cover this if you want to search for local minima or local maxima. You take the derivative dc by dx, and you equate this equal to 0, right? This is at the minimum value or maximum value, the minima, local minima or local maxima. Derivative, first derivative equal to 0, and you can go to the second derivative, and if it is greater than 0, so it becomes minimum value. If it is less than 0, it becomes a maximum value. You still remember this calculus? To get the minimum or maximum value?
Yes.
Okay, you get the first derivative equal to 0, second derivative.
Yes, it was not 1 1.
اوكي طيب ده احنا يعني رجعنا ورا جامد. اوكي so احنا here we will not consider only one variable. يعني here we have only one variable which is x, but definitely when we want to implement this on the economic dispatch problem, لا الاكس دي represent what in economic dispatch. يعني this x here in this simple example represent what in economic dispatch?
Load.
Huh? Represent
load.
what? Who's talking? If you raise your hand, then we become it. يعني X in this simple example that we want to implement it in an economic dispatch problem. So Mansoor Muhammad, X represent what?
power of the load.
B load.
ايه.
Okay. طيب, does anybody have another answer or different answer, or all of you confirm?
What is the question, Doctor, again?
The question is this example. We say we minimize the cost. The cost equal to the cost here equal to x, c of x equal to x square. So if we need to minimize the cost here, and we found out in the x equal to 0, and so we solve this one. This x in economic dispatch problem, what are the variables that we need to search for in order to minimize the cost? This x in economic dispatch represent what?
Generated power.
Okay, this is another solution, LEC. Does anybody have another solution or another answer? Ali Abdul Rauf?
Consumed power. Consumed energy.
You mean BL يعني load power?
No, the energy.
لا يعني we will stick with the power. يعني احنا when we have the economic dispatch, we need to search for the power of the generators, not the energy. Okay. يعني dispatch will be on the power, not energy.
Only real power.
Real power, yes, of course. طبعا not reactive power. Reactive power has another story. So we can have also reactive power dispatch, but the the variables there are completely different. Variables there in reactive power dispatch, not the generator output of real power, but could be generator output of reactive power. You can have also a switchable capacitor banks. This also will affect the reactive power in the load system. And also if you have transformer tabs, if the transformer tab is not 1-to-1, in this case you can also have some reactive power sources through this transformer tab, and this is also another source of reactive power. A reactive power problem is completely different than what we have here. Here we are targeting only the generator output power, real power, the real power output of the generator. So in economic dispatch, back to the question, in economic dispatch, what are the variables that we need to set or we need to find out? What are the variables? Do we need to find the load power?
No.
Definitely no. Why? لأن اللود power is independent. يعني أنت imagine that you are the power system operator. You are the power system operator. Can you control the load?
No, we can't control it.
The load is uncontrollable. And the load depends on the consumer. And I can go now and switch on the light, switch off the light. Some industrial plants switch on the factory. or disconnect the factory. So in this case, the power system operator should respond to this. Okay, what is in his hand. طبعا احنا ما بنتكلمش عن load shedding او ان الباور سيستم اوبريتور. طبعا الباور سيستم اوبريتور has also the authority to switch off loads if the system stability is becomes in question. يعني if the system becomes unstable or the frequency violates the limits, in this case we can go to load shedding. يعني ممكن الباور سيستم اوبريتور in order to keep the system stable it may يعني interfere and switch off some loads. This is what we call load shedding, but this at the critical situation. يعني مش يعني doesn't يعني implemented in it has not implemented in يعني regularly, but in critical states. But generally speaking احنا بنتكلم عن steady state problem. By the way, the economic dispatch is a steady state problem. System is running smooth, no disturbance, مفيش فولت مثلا، مفيش شورت سيركت، مفيش مثلا generator output or transmission line outage، مفيش حاجة. System is running smooth. فالباور system operator will look for what are the generated power from the generation station in order to minimize the cost. So الBL here is independent، بنسميها independent variable. BL independent variable. Okay, uncontrollable. The power system operator has nothing to do with it in steady state operation. Okay. So X here is PG. So we are looking for the power output of the generators in order to minimize the cost. This is the economic dispatch problem. So you have here an our problem BG1, you have here BG2, you have here BGN. So we need to find out how much these variables power generated in order to minimize the cost. Unconstrained parameter optimization from calculus, the first derivative equal to 0 and the local minima when the second derivative must be positive at the point of the local extrema. Yani this is the you solve this df by dx equal to 0, you solve. This is called extrema. Could be minimum, could be local minima or local maxima. So we call it in general extrema. So could be minimum, could be maximum. You have a function and this function is as such. So this is local minima, this is local maxima, this is local maxima, this is local minima, this is local maxima, and so on. For these are extrema points. This one, all these points are extrema, but if the second derivative is positive, then we are talking about these points. If the second derivative is negative, then we are talking about maxima, local maxima points here. So since the objective function is a cost, so the cost, of course, definitely we need to minimize. So it is, we are looking for the minimum value or local minima solution. So df by dx equal to 0 and the second derivative must be greater than 0 to have the local minima. Okay, if you have more than variables here, it's not only one variables. And you cannot say, you know, df, but here you can have the partial derivative. You can have partial f by partial x1, partial f by partial x2, partial f by partial x3. Yani this equation becomes a vector of equations, vector of equalities. Yani partial f, this is for x1, for x2, for x3, for x4. All these x's, the partial derivative equal to 0. And in this case, you have some, number of equations you need to solve. Not only one solution, not only one equation. So for a set of parameters x1 up to xn, the gradient of f vanishes at local extrema. Partial f by partial x I equal to 0. I varies from 1 to n. So you have here n equation, n number of equations. To be a local minima, the Hessian matrix، لأنه احنا بنتكلم عن several variables, not only one variables. لو هي one variables فيبقى d square f by dx square greater than 0. That's fine. This is, we have only one variable. But if we have more variables, or a number of variables, which is the case in our problem. In our problem, we are not have only one generator. We have dozens of generators, hundreds of generators. So we have hundreds of variables here. So in this case, the second condition here becomes the Hessian matrix. Hessian matrix must be a positive definite matrix. That means you have the eigenvalues of the Hessian matrix is positive. So if you solve these equations and you find x1, x2, x3, and so on, and you take that you find here and substitute with the Hessian matrix, and you calculate the objective function, you calculate the eigenvalues of the Hessian matrix, and you find it positive, then these variables satisfy the minimum or the local minima that you are looking for. So when you construct this Hessian matrix, you have, this is for x1, second derivative for x1, second derivative for x1, x1, so x1 square, second derivative for x1, x2, x1 up to xn. Okay. I don't know what is this. Abdul Aziz, mute yourself يا عبد العزيز. انت بتسمع اخبار ولا بتسمع مسلسلات ولا بتسمع Okay. So you need to construct the Hessian matrix if you have more than one variables. So this condition will be a matrix as such. You would get the second derivative with respect to x1 and x1, x2, x1 x up to xn, and you have here x2, x1, you have here x2 square, and so on. So the eigenvalues of this matrix, lambda of h, must be positive, greater than 0. If all the eigenvalues of the matrix is greater than 0, يبقى this is local minima solution. يعني we just expand the problem to include more variables, not only one variable we are looking for. Assume very simple example, minimize the cost, and this cost function is defined as x1 square plus 4x2 square minus 2x1 x2. So can we solve this equation? Can we have the values of x1 and x2 that gives you the minimum value of the cost? Necessary conditions for optimality, and the first derivative should be equal to 0. So you take the derivative with respect to x1, you take the derivative with respect to x2. So this is 2x1 minus 2x1, this derivative will be 0, so minus 2x2, derivative of x1 here equal to 1. And this is partial c by partial x2, which is this one will be 0. And this will be 2 times 4, so 8x2, and this is minus 2x1. So minus 2x1 plus 8x2. Can you solve these equations simultaneously? مش عارف ده automatically it should be okay. Can we solve these two equations simultaneously? Yeah, of course. These are two equations and two unknowns, x1, x2. So in principle, we can solve. But definitely, if there is no here, the absolute term, in this case, the only solution is x1 equal to 0 and x2 equal to 0. Okay, if you solve these equations simultaneously, you will end up with this solution. So this is called the stationary or extrema point. But we need to identify this stationary point or extrema point, whether it is minima or maxima. What will differentiate?
We need to find the
eigenvalue of Hessian matrix, or simply the second derivative as we have earlier. So let us construct the Hessian matrix. The Hessian matrix is very simple. This is partial C by partial x1. We can find partial C by partial x1 square. So you take the derivative again with respect to x1. So this becomes 2, and this term will become 0. Partial C by partial x1 partial x2. Can you take the derivative of this with respect to x2? So this will be 0 and this will be minus 2. And this one also will take it with respect to x1. So it becomes minus 2 and this is 0. And with respect to x2 again, this will be 0 and this will be 8. So this will be, as we here have, minus 2 and 8. So the Hessian matrix now is 2, minus 2, and minus 2, and 8. For this simple matrix 2 by 2, can you get the eigenvalues?
Yes.
Lambda I minus A equal to 0. And you solve for lambda. This is identity matrix, layer 2 by 2. And this is the matrix A or H, whatever. So you solve this determinant equal to 0 gives you the eigenvalues. So this is what we will do here. So this is the Hessian matrix as we construct. And the eigenvalues of this is just lambda I minus A or minus H. And you get the determinant equal to 0. The determinant of this matrix is lambda square. Lambda I will be lambda square and so on. Lambda square minus 10 lambda plus 12 equal to 0. If you solve this equation for lambda, you will end up with lambda equal to minus b plus minus square root of b square minus 4ac over 2a, second order equation, and this is simply the solution. So the square root of 52 is definitely less than 10. So 10 plus 5, and this could be 7 مثلا, 7 point something. So 10 plus 7, 10 minus 7, in all cases, lambda greater than 0. So the eigenvalues of the Hessian matrix is greater than 0. And it is equivalent to d square, df square by d square f by dx square is greater than 0. So that means that this is the condition for local minima. So the solution here is 0, 0. This solution gives us the local minima, or the minima point. Okay? Any question? So eigenvalues should be greater than 0 in order to have the minimum values. The stationary point is a minimum point. Let us expand the problem to have 3 variables, x1, x2, x3. In this, what is the order of Hessian matrix? What is the order of Hessian matrix?
3 times 3.
3 by 3. It is partial f square by partial x1 square, partial square f by partial x1 square, partial square f by partial x1 x2, and by partial x1 x3. and so on. So of course you can get the first partial f over partial x1. This equal to 2x1. This will diminish. This will diminish, and you have here x2. If you take the derivative with respect to x1, so this will diminish also. This becomes minus 8, and this is partial f by partial x1. This is equal to 0. Partial f over partial x2, you can get the derivative, very simple. This is equal to 0. Partial f over partial x3, also equal to 0. Here you have 3 equations and 3 unknowns, x1, x2, x3. In principle, you can solve these equations simultaneously to get x1, x2, x3. So you need to find x1, x2, x3 to solve this, the solution of this equation. And this is, I think, it's very simple. Ali Muhammad, do you have a question?
Yes. What does each variable in this equation represent in the economic spatial problem?
Each term you mean?
Each x variable.
Yeah, x value, this is BG1, let us say this is BG1, this is BG2, this is BG3. Actually, in economic dispatch, we don't have BG1, BG2 term. Okay? Yani we don't have in economic dispatch, the cost of generator 1 is alpha 1 plus beta 1 BG1 square, BG1 plus gamma 1 BG1 square. And the cost 2 is again alpha 2, B2, and so on, BG2, and so on. We don't have this term, the similar term in economic spatial problem, but this is just an example. We have this term, definitely. This is BG1, and this is BG2, and this is BG3. And yeah, of course, we don't have an economic spatial problem such a term. But in general, X represent variable, X2 another variable. So in our problem, which is economic spatial, are BG1, BG2, BG3 up to BGN. So this is our variables in economic spatial problem. Okay? Clear, ya Ali?
Clear.
Okay. So in principle, you can solve these 3 equations. You can have AX equal to B matrix form. You can find it as such, and then you can get the inverse of A. So X equal to A inverse times B. So you can solve the solution for X1, X2, X3. Of course, you can manage, and I think solution of these equations is straightforward. X1 in terms of X2, and you substitute here, and then and so on. But this is very simple. So let us solve this for X1, X2, and X3. And the second step is to find whether this solution is local minima or local maxima. Now we need to minimize. So we have to get Hessian matrix and the eigenvalue of the Hessian matrix, and this eigenvalue must be positive in order to say, this is the minimum value, or this is the minimum solution. So solving in matrix form, you can form AX equal to B, and then you can get the inverse of A, and you can get the solution as such. 3, 5, 2. This is the solution. So what we will do is we need to construct the Hessian matrix. The Hessian matrix, of course, from this derivative, we get partial square f over partial x1 square. So how much the value? What is the value of the element here, or the entry here?
2.
2, exactly, yes. Then you take the derivative with respect to x1 again. So this will diminish, and this one will be 2. What is the entry here?
1.
Exactly. This is partial square f or partial x1, partial x2. So you take the derivative with respect to x2, this will be 0, this will be 0, so this will be 1. And the third entry, and for x3, partial f by partial x3, 0. And you can definitely continue as such. So this is the Hessian matrix constructed, and you need to get the eigenvalue. So lambda I minus h, determinant of lambda I minus h equal to 0. So you can get here lambda I minus h. Of course, طبعا this is the third order. فيعني of course you can do in MATLAB, you can have this this matrix, and you can get the eigenvalue of this matrix. So the eigenvalue of this matrix is 1.55, 4, and 6.45. All of them are positive. That means in the solution that we find here, solution is 3, 2, 5. And this solution 3, 2, 5 gives, and these are positive, it gives the minimum value or minimum cost. Okay, so these are the variables that gives you the minimum cost. How much the minimum cost? How much the minimum cost? Well, cost at 3, 2, 5. Can you calculate it? يعني احنا قلنا ان this is the solution that gives you the minimum cost. Now we want to find out what is the minimum cost. We can go back to the cost function at the beginning here, and we substitute x1 equal to 3, x2 equal to 5, x3 equal to 2, and you substitute here 352 or 325, sorry, 325, and then you will find the minimum cost equal to 2. So this is the minimum cost that you have, and this is the solution. خلي بالكم, this is the solution. يعني this is the solution. 325 represents the solution that gives you the minimum cost. Okay, any question? Ahmed Makki?
Doctor, what we have the maximum?
Here in this equation, okay, let us take this function. خلينا ناخدها one variable in order to make it يعني clearer. So for this variable, for this equation, do we have maximum for this parabola?
No.
Do we have max? No. So we have only this one. Okay. Is it clear? And
Yes,
we have
yes.
only local minima. What we have here, local minima, which is this value. Type in this function, do we have local minima for this function?
Local maximum.
Do we have local maxima? Where is it? This is the function.
Okay.
local minima all of them دكتور.
لا هو ما فيش يعني you cannot say انه local minima. يعني فين اللوكال minima? Where is the local minima? This is called inflection point. We may have also a second derivative equal to 0. d square f by dx square equal to 0, and the df by dx equal to 0. يعني this will satisfy the necessary condition in df by dx equal to 0. But if you have d square f by dx square, or the eigenvalues, if you have more than one variable, equal to zeros, in this case, this is not la local maxima or la local minima, but this is called inflection point. Inflection point or saddle point. يعني. Okay. When we have these values here, the lambda equal to 1.5514 and 6.45 يبقى this is greater than 0 يبقى definitely this is the only local minima that we have in this function. هي the point is يا اللي بيسأل انه لو في السكند ديريفاتيف الهيشم ماتريكس نفسها function of x يعني you can say مثلا لو دي x1 كيوب مثلا لو دي x1 كيوب ماشي هيطلع لك هنا 2x1 او 3 whatever the coefficient is not an issue now. This will be x square, right? واضح؟ When you get the second derivative, this will be x1 here. And this could be function of x1, x2, x3. So الهيشم ماتريكس نفسها ما تبقاش constant بالصورة دي. إنها ممكن تبقى function في الx. وبالتالي when you have more than one solution here, when you have one طبعا this will be طبعا of course this will be a function of x square and this will be a function of x1 square, x2 square and so on. يعني that becomes here very difficult to solve, but you will find out more than one solution if these are function quadratic function. Are you following يا شباب؟
Yes.
لو دي more complex cost function وطلع لنا ان الايكويشنز دي function of x's, so you have different x square and x1, x2 and so on. You have more than one solution, and when you get H matrix, also H matrix is a function of x's, so you will substitute with this one and you find the eigenvalues. You will substitute with this one solution and you find the eigenvalues and so on, and in this case you will see which one gives you lambda greater than 0. Is it clear?
Doctor, it is 31.
Okay, so let us move to the quiz. Okay, so the quiz is almost 15 minutes, and you have to start within 5 minutes. I'll make it available. Set the time. Display. Okay, display until 1:37. After 1:37, the quiz will disappear, so you cannot access it after 5 minutes from now. You have to start right away. So it is available now.
Yes.
Yes, it's available, Doctor.
Okay, great. So I will